Tonight, we are going to look at a planet that should not exist. Not by the logic your instincts apply to the word planet. Not by the mental image you carry from every astronomy diagram you have ever seen. There is a world out there orbiting another star that is so large it forces you to reconsider what a planet is, what a star is, and whether the universe is even playing by the rules you thought it was. This is not a hypothetical. It is not a simulation or a thought experiment. It is a real object. Already found, already measured, already confirmed. And its size is the part that does not sit right, no matter how many times you read the number. By the end of tonight, you will understand how we find planets around other stars, why the largest ones push against the boundaries of what physics allows, and what it means to stand inside a universe where something this large is apparently possible. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something you already know. Jupiter is the largest planet in our solar system. If you have ever seen a diagram of the planets arranged by size, Jupiter is the one that makes everything else look like a rounding error. Earth fits inside Jupiter roughly 1300 times. All 7 other planets in the solar system, Mercury through Neptune, could fit inside Jupiter simultaneously with space remaining. Saturn, the second largest planet, has a volume of roughly 760 Earths to Jupiter's 1300. The gap between first and second place is enormous by any ordinary measure. Jupiter is a gas giant, meaning it has no solid surface in the way Earth does. There is no ground you could stand on. As you descended through Jupiter's atmosphere, the gas around you would grow denser and denser, eventually becoming a liquid, and then, under enormous pressure, the hydrogen would transition into a state that conducts electricity like a metal. The transition between gas and liquid and conducting states is gradual, not a sharp boundary, and the exact interior structure of Jupiter is still being refined by ongoing research, including data from the Juno mission, which has been orbiting Jupiter since 2016. Jupiter is so large that some astronomers have described it as a failed star, a body that had the right composition to potentially become something like the Sun, but never accumulated enough mass to ignite nuclear fusion at its core. This description is evocative, but requires care. Jupiter is primarily hydrogen and helium, the same elements that make up the Sun, but the mass required to initiate hydrogen fusion is roughly 80 times Jupiter's mass. Jupiter would need to be 80 times more massive to become even a small star. Failed star is a metaphor for a gas giant, not a technical description. That framing matters, because it draws a line. On one side of the line you have objects large enough to sustain nuclear fusion in their cores, stars. On the other side you have objects that are not large enough, planets and brown dwarfs. Jupiter sits comfortably on the planet side of that line. It is massive, but not massive enough. The Sun contains roughly 99.8% of all the mass in our solar system. Jupiter accounts for most of the rest. And yet Jupiter is still nowhere near the threshold at which it would begin to glow. Now hold that image. Jupiter as the outer limit of what a planet looks like. The biggest thing in the solar system that is not the Sun. Something so large it contains within itself more volume than all the other planets combined, by a wide margin. Because the planet we're going to talk about tonight makes Jupiter look like a marble. Its name is Roge 1315b. And when astronomers first measured its size, the number was hard to accept. Not because there was any obvious error, but because the number seemed to contradict what physical models of planetary formation said should be possible. A gas planet can only grow so large before additional mass actually causes it to contract rather than expand, because increasing internal pressure compresses the interior more efficiently than new mass puffs the exterior out. There is a ceiling. Physics builds one. Roge 1315b sits close to twice the radius of Jupiter. On its own, that sounds like a modest number. Double the radius. But a sphere that is twice the radius has 8 times the volume of the original. You are not looking at a planet that is twice as big as Jupiter. You are looking at a planet with roughly 8 times the interior space. Put 8 Jupiters inside one object, and you are still only partway to visualizing what we are talking about. Then remember that Jupiter itself holds 1,300 Earths. Scale upward from there. 8 Jupiters is over 10,000 Earths packed into a single object. This is where numbers start to lose their grip. The human brain has a specific relationship with scale. It can understand small differences and large differences at extremes, but in the middle range, at the scale of a planet, it tends to flatten everything into rough categories. Big planet, very big planet, very, very big planet. The differences between those categories start to blur the same way the difference between a million and a billion becomes conceptually indistinct, even though one is 1,000 times the other. Roge 1315b is not just a very big planet. It is a planet at a size that planetary science did not expect to find, and is still working to explain. The mechanism that inflates it involves its star in a way that most planets in our solar system never have to contend with. And that mechanism is the beginning of what makes this object genuinely uncomfortable to think about. Before we can understand what makes the largest known planet strange, we have to understand how planets are found at all. For most of human history, the only planets anyone knew about were the ones visible from Earth with the naked eye. Mercury, Venus, Mars, Jupiter, Saturn. The planets that ancient astronomers watched move against the background of fixed stars, whose motions were tracked carefully enough that their periods and approximate positions could be predicted, and which were woven into the mythologies and calendars of civilizations across the ancient world. The discovery of the outer planets came with better instruments. Uranus was found in 1781, when William Herschel, working systematically through a region of sky with a telescope he had built himself, encountered a point of light that showed a perceptible disk and moved against the background stars at a rate inconsistent with a fixed star. He initially thought it might be a comet, but the circular orbit confirmed it was a planet. Neptune was a different kind of discovery. The unexpected perturbations in Uranus's orbit, deviations from the path it should have followed given only the known planets and the Sun, pointed to an unseen source of gravity. Mathematicians Urbain Le Verrier in France and John Couch Adams in England independently calculated where the unseen body must be, and Johann Galle found it at the Berlin Observatory in 1846 within a degree of the predicted position. The story of those discoveries is a story of detection by proximity and brightness. The planets of our solar system are close enough and reflective enough that they show up in telescopes as objects with measurable positions and, for the largest ones, visible disks. Finding them was difficult by the standards of their era, but the objects cooperated by being large and relatively near. Planets around other stars cooperate in neither of those ways. The nearest star to Earth beyond the Sun is Proxima Centauri, about 4.2 light-years away. A light-year is roughly 10 trillion kilometers. The distances between stars are so enormous that even our best telescopes cannot separate a planet from its host star the way you might distinguish a stone lying next to a boulder. The star is hundreds of millions of times brighter than any planet it might host. The planet is tiny relative to the star. The angular separation between the two, as seen from Earth, is so small at interstellar distances that the planet is simply lost in the star's glare for any direct imaging approach. The challenge is not primarily one of resolution, though resolution matters. It is primarily one of contrast. Imagine standing a kilometre from a spotlight and trying to see a firefly hovering a few centimetres from the light source. The brightness difference is too extreme. The firefly exists, but it cannot be seen from that distance against the glare. Techniques for directly imaging exoplanets have been developed and refined, using coronagraphs to block the star's light and adaptive optics to sharpen the image. Direct imaging has successfully detected some massive young gas giant planets at large orbital separations from their host stars, where the contrast ratio is more favourable. But for hot Jupiters orbiting so close to their stars, direct imaging is not feasible with current technology. The orbital distance is too small and the contrast ratio too extreme. So the transit method, which does not try to see the planet but instead detects its effect on the starlight, became the dominant approach. So astronomers found other ways. The most productive method used to build the current catalogue of confirmed exoplanets is called the transit method. The idea is straightforward. If a planet orbits a star, and if the orbital plane of that planet happens to line up with our line of sight to the star, then at regular intervals the planet will pass directly in front of the star as seen from Earth. When it does, it blocks a small fraction of the star's light. The star dims slightly for a predictable duration at a regular period. That dimming is the fingerprint of a planet. The fraction of light blocked depends on the relative sizes of the planet and the star. For Earth transiting the Sun as viewed from another star system, the dimming would be about 1/100th of 1%, a tiny signal that requires extremely precise photometry to detect, and has only been detected for Earth-sized planets in recent years with space-based observatories. For a Jupiter-sized planet transiting a Sun-sized star, the dimming is about 1%. For an inflated hot Jupiter with twice Jupiter's radius transiting the same star, the dimming is about 4%. The larger the planet relative to the star, the deeper and more easily detectable the transit signal. This means that inflated hot Jupiters are among the easiest exoplanets to detect via transits. They are large, so they produce a deep dimming signal. They orbit close to their stars, so their orbital periods are short, and their transits repeat frequently, giving many opportunities for confirmation. And their close orbits mean that a higher fraction of them are geometrically aligned to transit as seen from Earth, because the probability of a transit depends on the ratio of the star's radius to the planet's orbital radius, and that ratio is more favourable at smaller orbital distances. Hot Jupiters are almost certainly not the most common type of planet in the galaxy. Statistical analysis suggests they occur around only a few % of Sun-like stars, but they were among the first exoplanets found, and among the best characterised because the detection methods favour them. The early catalogues of known exoplanets were dominated by hot Jupiters, precisely because the instruments of the time were most sensitive to the signals hot Jupiters produce. As instruments improved and observational baselines lengthened, smaller planets and longer period planets began to fill the catalogues. But the hot Jupiter Foundation, the first exoplanet type discovered, remains the best studied and most extreme class in many respects. ROJ 1315b's is the extreme among the extremes. The largest measured representative of a planet type that was itself a surprise, at a radius that pushed the models further than any other single confirmed object. The transit method does not take a photograph of the planet. It detects the planet's shadow. The The depth of the dimming tells astronomers how large the planet is relative to the star. A large planet blocks more light. A small planet blocks less. By measuring the exact percentage of light blocked, astronomers can calculate the ratio of the planet's radius to the star's radius, and from the known size of the star, they can work out the planet's size. The duration of the dimming tells astronomers about the planet's orbital speed, and from that, its orbital distance. The periodicity of the dimming, how often the dimming repeats, gives the orbital period directly. From the orbital period, through Kepler's laws of planetary motion, the orbital distance can be calculated again as an independent check. These measurements cross-validate each other. What the transit method does not easily provide is the planet's mass. Size and mass are different things, and the transit alone measures only size. To get mass, astronomers typically need a second measurement technique called radial velocity. This method measures the tiny wobble a planet induces in its host star as the two orbit their shared centre of gravity. The star moves toward and away from Earth at a speed that depends on the planet's mass and orbital parameters. By measuring this wobble in the spectrum of the star's light, using the Doppler shift in the positions of spectral lines, astronomers can calculate the planet's minimum mass. Together, transit and radial velocity provide both radius and mass, and from those two values, density. The density is what tells you what kind of object you are looking at. A rocky planet has high density. A water world has moderate density. A gas giant like Jupiter has density close to water. An inflated hot Jupiter has density far below water, sometimes dramatically so. This method has found thousands of planets. It found most of the confirmed exoplanets in the current catalogues. The Kepler Space Telescope, launched in 2009, stared at a fixed patch of sky containing over 150,000 stars for 4 years and found thousands of planetary transit signals. Its successor, TESS, launched in 2018, expanded coverage to most of the sky and has added thousands more candidates. And buried in all of that data, among all those planetary signals of all those sizes, is a population of planets that kept surprising the astronomers who measured them. They are large. Not slightly large. Not large with reasonable explanation. Large in a way that the physics of planet formation should not easily produce. Large in a way that requires a second mechanism beyond the one that formed them to explain. The largest planet we have found so far is one of these. And understanding why it is as large as it is requires understanding what that second mechanism is. The first thing you need to understand about planet formation is that it is a process with a size limit built in. Giant planets, the kind Jupiter represents, form primarily by accumulating gas. The process begins with a rocky or icy core that grows by collisions in the disk of material surrounding a young star. This phase, called core accretion, is slow. Dust grains stick together to form pebbles. Pebbles collide to form larger bodies. Larger bodies collide to form planetesimals, objects of kilometre-scale mass that then sweep up smaller debris as they move through the disk. The process takes millions of years before a core large enough to trigger the next phase exists. When that core reaches a critical mass, typically somewhere in the range of 10 to 20 Earth masses, it becomes massive enough for its gravity to pull in the surrounding gas rapidly. What was a slow accumulation of rock and ice becomes a rapid infall of hydrogen and helium from the disk. The planet grows quickly, puffing outward as more gas falls onto it. This phase is called runaway gas accretion, and it can add most of a gas giant's final mass in a relatively short time. But as the gas accumulates, something else happens. The gas is compressed by gravity. compression generates heat. The interior of the planet grows hot, and hot gas resists further compression. At some point, the pressure from the thermal energy inside the planet pushes back against the gravity, pulling new gas in. The planet settles into an equilibrium between the inward pull of gravity and the outward pressure from its heated interior. This is the same equilibrium that governs stars. In a star, nuclear fusion continuously generates heat in the core, and that heat provides the pressure that prevents the star from collapsing under its own gravity. The star burns as long as it can maintain that balance. In a gas giant, there is no fusion, but the heat from formation is still stored in the interior, and that heat provides pressure in the same way. A newly formed gas giant is actually larger than it will be later in its life, because as it slowly radiates its formation heat into space, it contracts. Jupiter today is smaller than Jupiter was when it first formed, by an amount that models can calculate. This equilibrium has a curious consequence for size. Once a gas planet reaches a certain mass, adding more mass does not necessarily make it larger. The additional mass compresses the interior more, which counters the effect of adding volume. For a wide range of masses above Jupiter, the planet's radius stays roughly constant. It gets heavier, but not much bigger. The radius plateaus. This plateau is not a gradual thing. It is a fairly sharp feature in the mass-radius relationship for gas giants. If you plot planetary radius against planetary mass for giant planets, the curve rises steeply at low masses, flattens out near Jupiter's mass, and then for very high masses actually turns downward as self-compression increasingly dominates. The most massive gas planets can actually be smaller in radius than Jupiter, because so much mass has compressed the interior. This is why Jupiter and Saturn, despite Saturn having less than a third of Jupiter's mass, have similar radii. Jupiter is more compressed. Saturn is more puffed out. They look similar in size from a distance, because the mass-radius relationship for giant planets is nearly flat across a broad range around Jupiter's mass. If this were the whole story, then the largest planet we would ever find should be roughly Jupiter-sized, maybe a bit larger, maybe 50% larger on a good day, depending on exact conditions during formation and the composition of the gas envelope. Roge 1315b is not 50% larger than Jupiter. It is close to twice the radius, which means close to 8 times the volume. It is a real object that orbits a real star, and its size is confirmed from multiple independent measurements, and yet it exists in a mass range where the standard formation model says it should not be that large. The question is not just how big this planet is. The question is what is making it that big, and the answer turns out to be the star itself. The answer involves the planet's star and the distance between them. Roge 1315b does not orbit its star the way Earth orbits the Sun. It does not trace a wide, slow path at a comfortable distance. It orbits in extremely close, completing one full orbit in roughly 3 days. For comparison, Mercury, the closest planet to our Sun, takes 88 days to complete one orbit. Roge 1315b completes an orbit in 3. At that distance, the star is not a distant warm presence, it is a furnace. The stellar radiation falling on Roge 1315b is hundreds of times more intense than what Jupiter receives from the Sun. The day side of the planet, the face permanently turned toward the star, is being irradiated at a level that would be completely destructive to anything resembling a temperate environment. The energy arriving from the star heats the outer atmosphere of the planet to temperatures of over 1,000 degrees. In some cases, for the hottest of these close-in giants, day-side temperatures reach several thousand degrees, comparable to the surface temperature of cooler stars. What this constant bombardment of energy does to the planet is called inflation. The heat from the star deposits energy into the atmosphere of the planet. That energy has to go somewhere. In the outer layers it drives strong winds, but deeper in the atmosphere, some of that energy works its way downward through the gas. And as it does, it prevents the planet's interior from cooling the way a planet at greater distance would. A giant planet that formed further from its star would radiate heat away over time, contracting slowly as it cooled. Roche 1315b cannot cool efficiently because the star keeps pumping energy in. The planet stays hot. Hot gas takes up more space. The planet stays large. This class of worlds, giant planets orbiting extremely close to their host stars, are called hot Jupiters. The name reflects two of their defining properties. They are roughly Jupiter-sized or larger, and they are at temperatures that no planet in our own solar system comes close to reaching. The first hot Jupiter ever confirmed was 51 Pegasi b, detected in 1995 by Michel Mayor and Didier Queloz using the radial velocity method. When the discovery was announced, many astronomers were skeptical. The planet had roughly half Jupiter's mass, but orbited its star in just 4 days. Formation models did not predict that a giant planet could exist so close to a star. Some researchers suggested it might be a misidentification, a stellar oscillation or binary star effect, rather than a true planet. Subsequent observations confirmed it was real. And within a few years, more hot Jupiters were found. They were not rare. They appeared to represent a few percent of planetary systems, which in a galaxy of hundreds of billions of stars means they exist in enormous numbers in absolute terms. The inflation of hot Jupiters, the fact that many of them were larger in radius than formation models predicted for their mass, became a separate puzzle once the systems were being measured in detail. The correlation was clear in the data. More irradiation from the star corresponded to more inflation in the planet. But the exact physical mechanism by which stellar radiation translates into planetary radius remained, and to some extent remains today, a subject of active research. Roche 1315b is among the most extreme of this class. Its proximity to its star, its irradiation level, and the resulting inflation of its atmosphere place it near the upper edge of what has been observed. It is a hot Jupiter that has been pushed by its star's heat to a size that pure formation theory would not predict. But the inflation alone does not explain everything. To understand why this planet ended up this close to its star in the first place, you have to understand something about how planetary systems rearrange themselves after they form. Planets do not necessarily stay where they form. This is one of the more unsettling results of the exoplanet era. The intuitive picture of planetary formation has a star forming at the centre, a disk of gas and dust surrounding it, and planets condensing at different distances according to what the temperature allows at each location in the disk. Ice giants form far out where it is cold enough for water and methane to freeze. Gas giants form somewhat further in than the ice giants, but still beyond the snowline, the distance at which water ice can exist as solid. Rocky planets form close to the star where temperatures are too high for volatile compounds to condense. The picture is tidy. It is also incomplete. In our own solar system, there is strong evidence that the planets did not all form where they currently sit. Jupiter and Saturn appear to have migrated inward and then outward during the early solar system, under the influence of their gravitational interactions with the gas disk they formed in. One model of early solar system history, called the Grand Tack hypothesis, suggests Jupiter migrated as far as 1.5 astronomical units from the Sun, well inside where Mars currently orbits, before being caught by a gravitational interaction with Saturn and pulled back outward to roughly its current position. The tack in the Grand Tack refers to the sailing term for reversing direction. This inward-outward migration of Jupiter, if it happened, would explain several puzzling features of the inner solar system. It would explain why Mars is so much smaller than Earth, because Jupiter's inward passage would have swept material out of the region where Mars was forming, starving it of the mass needed to grow larger. It would explain why the asteroid belt is so depleted relative to the mass expected from a normal disk. And it would explain why the inner solar system's rocky planets are arranged as they are. If the Grand Tack hypothesis is correct, our solar system experienced a version of giant planet migration, just not as extreme as what happened in hot Jupiter systems. Jupiter stopped and reversed. In hot Jupiter systems, the giant planet did not reverse. It kept going until it arrived at close orbital distance. The architecture of our solar system today, with the giant planets at their current distances and the asteroid belt in its depleted state, may be the aftermath of that early migration, a migration that was severe enough to reshape the inner solar system, but not severe enough to strip it entirely. For systems with hot Jupiters, the reshuffling was more dramatic. A giant planet cannot form at the orbital distance where hot Jupiters are found. The temperatures so close to a star are too high for the volatile ices and compounds needed to build a large core to condense into solids. The material budget for a giant core simply does not exist that close to a star. The hot Jupiter must have formed further out in a cooler region of the disk, and then migrated inward. Something moved it. The leading explanation for this migration involves the disk itself. As the planet formed in the outer disk, it was not simply floating in empty space. It was embedded in the gas and dust of the protoplanetary disk, interacting gravitationally with the material around it. As the planet moved through the disk, it created a wake of density waves in the gas ahead of and behind it. Those waves exerted a net gravitational force on the planet, and under most conditions during disk formation, that force pointed inward. The disk acted as a brake, draining the planet's orbital energy and drawing it toward the star step by step over timescales of a few million years. This process is called Type II migration, and it operates specifically for planets massive enough to open a gap in the disk around their orbit. A planet that massive clears a lane of material from the disk as its gravity captures material that would otherwise flow across the gap. The planet and the gap then migrate together inward as the disk material exterior to the gap flows slowly toward the star under the disk's own internal viscosity. The planet rides the inward flow of the disk like a ship being carried by a current. The timescale for this migration depends on the disk's properties. A massive, viscous disk can migrate a planet from several astronomical units down to a close-in orbit in a few million years. For context, the Sun and planets are about 5 billion years old. A few million years is a small fraction of a planetary system's lifetime. The migration can happen early, before the disk disperses, and can be effectively complete long before the system settles into its long-term configuration. The migration stops, or the planet is stranded at close distance when the disk disperses. Protoplanetary disks do not persist indefinitely. Radiation from the host star, stellar winds, and other processes gradually erode the disk from the inside out. Once the disk is gone, the mechanism driving migration is gone. The planet is wherever it is when the music stops. There may also be a competing mechanism that prevents some planets from reaching the star itself. As a planet migrates very close to a star, the star's magnetic field can interact with the inner disk in ways that create a pressure barrier that slows or stops the infall of disk material, and therefore the migration. Hot Jupiters may pile up at the orbital distance where this process operates, which would explain why the observed distribution of hot Jupiter orbital periods shows a concentration around 3 to 5 days, rather than a smooth distribution all the way down to orbital periods of hours. By the time the disk dissipated around Rho G3 1315b's star, the planet had arrived at close orbital distance and was locked in. The star's gravity held it there. The disk was gone. There was nothing left to push it further in or pull it back out. The planet settled into its close orbit and has been completing it every 3 days since, for as long as the system has been in its current state. For Rho 1315b, the inward migration brought a Jupiter-class world to a position where the stellar radiation was intense enough to inflate it substantially beyond what formation alone would have produced. The formation history and the final size are connected through the orbital history. The planet formed where cold conditions allowed a massive core and gas envelope to accumulate. It migrated to where heat conditions continuously added energy to that envelope, and it arrived at its current size as the result of both processes working in sequence, one after the other, over millions and then billions of years. A world created far from its star, dragged close enough to be rewritten by it, and then held there ever since. The star that Rho 1315b orbits is not the Sun. This matters in ways beyond simple comparison. The star determines nearly everything about what the planet experiences. Its temperature, its radius, the intensity of its radiation output, the kind of light it emits, the magnetic field it generates, the stellar wind it blows outward into the system. For a planet at the orbital distance of Rho 1315b, the star is not background. The star is the defining fact of the planet's existence. A star of this type produces light across a broad spectrum. Most of the energy output is in visible and near-infrared wavelengths, and it is this light that heats the planet's day side and drives the atmospheric circulation. But stars also produce radiation at much shorter wavelengths, ultraviolet light and X-rays, in smaller quantities. That shorter wavelength, higher energy radiation does something different to the upper atmosphere. Short wavelength radiation carries more energy per photon. When a photon of ultraviolet or X-ray light strikes a molecule in the upper atmosphere of a planet, it can deposit enough energy to ionize the molecule, stripping away electrons, or to heat the gas directly to temperatures far above what the visible light radiation achieves at lower levels. The result is an extended, extremely hot layer at the top of the atmosphere called the thermosphere or the exosphere, where temperatures can reach many thousands of degrees even on planets far from their stars. At Rho 1315b's orbital distance, this upper atmospheric layer is not just hot, it is moving. The gas molecules in the upper atmosphere, heated to extreme temperatures and sitting at the top of a gravity well that is weaker than Jupiter's due to the planet's inflated size, acquire speeds that can exceed the local escape velocity. Escape velocity is the speed at which an object has to move to completely break free from a body's gravitational pull. When gas in the upper atmosphere moves faster than this, it simply leaves. It flows away from the planet into the space between the planet and the star, swept along by the stellar wind. This process is called atmospheric escape, and for hot Jupiters it is sometimes observed directly in the form of extended hydrogen clouds around the planet that have been detected during transit observations. Some hot Jupiters appear to have comet-like tails of escaping gas streaming away from them in the direction away from the star, pushed by radiation pressure. For smaller planets at close orbital distances, photoevaporation can strip away an entire gas envelope over billions of years, leaving behind only a rocky or water core. This is thought to explain a feature of the exoplanet population called the radius gap, a shortage of planets at sizes between roughly 1.5 and 2 times Earth's radius. as if planets in that size range are unstable against photoevaporation and tend to either lose their envelopes entirely or retain enough to remain larger. For a giant planet like Roge 1315b, with its enormous gravitational reserve, the mass loss from atmospheric escape is unlikely to fundamentally change its nature over the remaining lifetime of its star. But it is still happening. The planet is not static. Its outer atmosphere is continuously bleeding away into the space between it and the star, carried off by the same radiation that is simultaneously heating the layers below and keeping the planet inflated. The star gives with one hand and removes with the other. The planet exists in the balance between the two. There is one more effect of the close orbital distance that changes the nature of this world in a fundamental way. Rotation. The star matters as much as the planet. Everything about Roge 1315b, its current size, its temperature, its atmospheric chemistry, its orbital dynamics, its future, is shaped by the properties of the star it orbits. The planet did not choose its star. It ended up there through the mechanics of formation and migration, and whatever star was at the center of its system when it formed and migrated became the dominant fact of its existence. The star Roge 1315b orbits is roughly Sun-like in spectral type, a main sequence star that fuses hydrogen in its core as the Sun does, producing energy that radiates outward as light. The Sun has been burning this way for about 5 billion years and is expected to continue for roughly another 5 billion before its core hydrogen runs out and it begins to expand into a red giant. The life cycle of the host star matters for the planet because the two are linked. While the star is on the main sequence burning hydrogen steadily, the conditions the planet experiences are relatively stable. The star's luminosity changes slowly over billions of years as its internal composition shifts, generally becoming gradually more luminous as it ages. For a planet as close to its star as Roge 1315b, even small increases in stellar luminosity over time translate into increased irradiation and increased atmospheric inflation. But the more dramatic change comes at the end of the star's life on the main sequence. When a Sun-like star exhausts its core hydrogen, it transitions into a red giant. The outer layers expand dramatically, and the star's radius can grow to hundreds of times its current size. For planets orbiting in the inner system, this expansion is fatal. Mercury and Venus will almost certainly be engulfed when the Sun becomes a red giant billions of years from now. Earth may be at the edge of survival, depending on the exact dynamics of the expansion and how much mass the Sun loses in the process. For Roge 1315b, orbiting at its extremely close distance, engulfment by the expanding red giant is effectively certain if the star follows a typical evolutionary path. The planet will be swallowed. The gas giant's material will be incorporated into the outer layers of the expanding star, and whatever remains of the planet after the star has evolved further will eventually disperse into space along with the star's outer layers when the red giant sheds them to form a planetary nebula. There is a kind of symmetry in that end. The star made the planet large. The star will eventually take it back, but this is billions of years in the future. On the timescale that matters to an observer today, the star is steady, the planet is orbiting, and the system is producing data that is reaching Earth right now, carried in the dips of starlight that pass through our telescopes every 3 days when the planet crosses the face of its sun. A planet orbiting this close to its star does not spin freely. In our solar system, Earth rotates roughly every 24 hours independent of its orbital period around the Sun. The two motions, the rotation and the orbit, are independent. Earth spins at its own rate, driven by the angular momentum it carried when it formed. and that rate has been only slightly slowed by the tidal influence of the Moon over billions of years. The Moon is different. The Moon's rotation has been slowed and locked by Earth's tidal forces over billions of years, so the Moon rotates exactly once per orbit. The same face of the Moon always points toward Earth. The far side is permanently turned away. This is called tidal locking, and it is not coincidence or magic. It is a predictable outcome of the mathematics of tidal friction. When a large body orbits a smaller one, or in the case of most planets, when a small body orbits a large one, the gravity from the primary body is slightly stronger on the near side of the orbiting body than on the far side. This difference in gravitational pull across the body's diameter is called the tidal force. The tidal force stretches the orbiting body slightly, creating a bulge on the near side and a corresponding bulge on the far side. If the orbiting body is rotating at a different rate than its orbital period, the bulges are not perfectly aligned with the line between the two bodies. There is a slight offset. That offset creates a gravitational torque that gradually slows the rotation until the rotation rate matches the orbital period. At that point, the body is tidally locked. The same process operates between a star and a close planet, but with far greater force. The tidal force that a star exerts on a planet decreases with the cube of the distance between them. Halve the distance and the tidal force increases by a factor of 8. At the close orbital distances of hot Jupiters, the tidal force is enormous, and the timescale for tidal locking is far shorter than the age of the planetary systems. Roge 1315b, orbiting its star in roughly 3 days, almost certainly rotates in roughly 3 days. One face of the planet permanently faces the star. One face permanently faces away. Think about what that means for a world of this size. The day side, the face permanently turned toward the star, receives continuous, unrelenting irradiation. It is being bombarded by stellar radiation every moment of the planet's existence, without relief, without a night cycle, without any rotational period to spread the heat around. The temperatures on the day side are among the highest of any planetary atmosphere known. Some hot Jupiters have dayside temperatures high enough to vaporize iron. The clouds that form on their daysides are not water clouds. Depending on the temperature, they may be silicate clouds, clouds made of minerals that are solid rock at Earth surface temperatures but become liquid droplets in the extreme heat of the dayside atmosphere. The night side is a different world. On the side permanently facing away from the star, no direct stellar radiation arrives. The night side cools, but it does not cool to anything like the temperatures of our outer solar system, because the atmosphere of the planet is not static, it circulates. Massive winds, driven by the enormous temperature difference between the endlessly scorched day side and the relatively cooler night side, carry energy around the planet from the hot side toward the dark side. These winds can reach several thousand kilometers per hour, moving through the transition zone between the two hemispheres at speeds that dwarf anything in Earth's atmosphere. For some hot Jupiters, the atmospheric circulation is efficient enough that the temperature difference between the day side and the night side is modest. Infrared observations from space telescopes have mapped the temperature patterns of some of these worlds by tracking how their thermal emission changes as they orbit. Some show hotspots not exactly at the substellar point. The spot directly below the star, but slightly offset, shifted downwind by the atmospheric circulation. For others, the circulation is less efficient, and the two hemispheres develop strongly different temperature profiles. The day side glows intensely in infrared. The night side is dramatically cooler. The result is a planet divided, permanently split into a hemisphere of heat and a hemisphere of relative dark. No sunrise, no sunset, no daily rhythm, no seasonal cycle. Just the same face baking under the same star, endlessly, while the other face turns its back on all that light and exists in a permanent wind-torn night. For a planet of this size, for something roughly 8 times the interior volume of Jupiter, the scale of that division is immense. The boundary between the hemispheres, the terminator where day permanently becomes night, runs the entire circumference of the planet. On Earth, the terminator is a sweeping line that crosses the globe twice a day as the planet rotates. On Roge 1315b, the terminator does not move, it sits in the same position forever. The permanent boundary of 2 permanent worlds squeezed into one. The circumference of Roge 1315b, given its radius of roughly 140,000 kilometers, is about 880,000 kilometers. The terminator, the line dividing the permanent day from the permanent night, runs that full distance around the planet. Along that boundary, the conditions are transitional. Neither the extreme heat of the direct substellar point nor the complete absence of direct radiation on the night side. The temperature gradient along the terminator drives the powerful winds that carry heat from the day side to the night side, and those winds follow the terminator boundary like a river following the edge of a continent. On Earth, the border between day and night is experienced as twilight, a brief period of changing light as the sun moves below the horizon. It is temporary and cyclical. On Roge 1315b, the transition zone is permanent and fixed. There is no dusk on the night side. There is no dawn on the day side. The transition zone simply is unchanging for the entire lifetime of the planet in its current orbital state. This is a world where the 2 most fundamental rhythms of Earth life, day and night, simply do not apply. The concept of a day, the rotation of a planet carrying any given point from darkness into light and back again, is so fundamental to life on Earth that it is built into the biology of almost every organism. Circadian rhythms, the internal clocks that regulate sleep, waking, hormone cycles and cell division, are present in organisms from single-celled cyanobacteria to humans. They evolved in response to the predictable cycle of sunlight and darkness that Earth's rotation creates. The day is not just a unit of time. It is a physical fact that life has been responding to for billions of years. On Roge 1315b, the rotation period equals the orbital period, and neither changes meaningfully on any timescale. There is no day cycle. The star is always in the same position. The light never changes. The darkness on the night side never changes. Whatever chemistry might exist in the atmosphere of this world, and at its temperatures, it is difficult to imagine anything recognizable as biochemistry. It would exist in conditions that have no analogue to the cycling light environment in which Earth's biology evolved. This is a planet where the clock stopped at birth. Not because time stopped. The planet ages. The star evolves. The atmospheric chemistry changes slowly. The mass loss continues. Time passes in the planet's history the way it passes in any physical system. But the daily experience of that time, the rhythm that on Earth structures everything from cell division to the weather, is absent. The planet exists in a kind of perpetual noon on one side and perpetual midnight on the other, with the fierce transition at the terminator the only dynamic boundary available. The scale and the conditions together produce an environment unlike anything in the solar system we studied first. This is the world that the universe made here. The boundary between the largest planets and the smallest stars passes through a strange region of objects. Brown dwarfs are often described as objects too large to be planets, but too small to be stars. The description is accurate as far as it goes, but it leaves out what makes brown dwarfs interesting in their own right. they form differently from planets. Rather than accumulating from small particles in a disk, they form from the direct collapse of gas clouds, the same process that forms stars, but with insufficient mass to reach the conditions needed for sustained hydrogen fusion. They glow in infrared from the heat of their formation, slowly cooling over billions of years as they radiate away their internal energy. The oldest, most massive brown dwarfs can look like warm gas giants. The youngest, most massive ones can look like cool dim stars. They are genuinely intermediate objects, not just definitionally intermediate, but physically intermediate, with some properties of stars and some properties of planets. Brown dwarfs span a wide range of masses, from just above the deuterium burning threshold at roughly 13 Jupiter masses to nearly 80 Jupiter masses, where hydrogen fusion in the core begins to operate. Within that range there are subclasses L dwarfs, T dwarfs, and Y dwarfs, ordered by decreasing temperature, with the coldest Y dwarfs having temperatures not much above those of the hottest known gas planets. In the early years of exoplanet discovery, astronomers noticed something peculiar in the radial velocity surveys. While planets were being found around many stars, and while binary companions were being found at a range of masses, there was a puzzling gap in the companion mass distribution. Companions with masses between roughly 13 and 80 Jupiter masses in the brown dwarf range appeared to be much rarer as close companions to Sun-like stars than either planetary mass companions below 13 Jupiter masses or stellar mass companions above 80. This gap is called the brown dwarf desert. It suggests that the processes that produce planets and the processes that produce stellar companions are different, and that they operate at different mass scales with a gap between them. Planets form in disks around stars, building up from small bodies. Binary stars form by the fragmentation of a collapsing molecular cloud into two centers of gravity that collapse separately. Brown dwarfs formed by direct collapse can become binary companions at large separations, but at close orbital distances like those of hot Jupiters, the companion formation mechanisms that would produce brown dwarf companions appear to be inefficient. Roge 1315b at 1 to 2 Jupiter masses is well below the brown dwarf desert. It is a planetary companion by mass, formed in a disk, migrated inward, and inflated by stellar radiation. But its radius, approaching the size of some brown dwarfs, makes it an interesting object to compare to the brown dwarf population. The largest brown dwarfs can have radii somewhat larger than Jupiter's. The youngest, hottest brown dwarfs are larger because they have not yet contracted as much. But brown dwarfs do not have their size artificially maintained by stellar irradiation the way Roge 1315b does. They cool and contract over time, following their own internal thermal evolution. A brown dwarf of 1 billion years of age is significantly smaller than it was when it formed. An inflated hot Jupiter stays at its inflated size for as long as the irradiation continues. Roge 1315b's is not a brown dwarf. Its mass is planetary and its formation history is almost certainly disk-based rather than collapse-based. But the question of what kind of object it is, a planet at the extreme of what planetary inflation can produce, illuminates how the categories of planetary science are still being refined by the objects the universe is willing to make. The line between a gas giant and a brown dwarf is a mass line, not a size line. Roge 1315b has planetary mass and giant star fraction radius. A young, massive brown dwarf might have similar radius, but would have many times more mass. The two objects would look similar in a radius-only measurement, but tell very different stories in a mass and radius measurement. This is why the radial velocity follow-up, the mass determination, matters as much as the transit discovery. Knowing the radius without the mass leaves the classification ambiguous. Knowing both resolves it. For Roge 1315b, both are known. It is a planet by mass. It is enormous by radius. It occupies a region of parameter space that earlier models did not fully anticipate, and its existence there has contributed to a more complete understanding of what the combination of disk formation, orbital migration, and stellar irradiation can produce. The universe made something that sits at the edge of one category and points toward another, while belonging clearly to neither in terms of origin. That kind of object is often the most useful kind for science, the one that tests the boundaries of existing frameworks and forces them to expand. There is a question that comes up naturally when astronomers discuss the largest gas planets, and it is a question the title of this script has already suggested. At what point does a very large planet stop being a planet? The answer is not as clean as the question implies. There is no bright line in the physics that separates a planet from a brown dwarf or a brown dwarf from a small star. There are definitions, but they are human conventions imposed on a continuous spectrum of objects, and they are contested at the edges. The current working definition used by the International Astronomical Union defines a planet, in the context of our solar system, as an object that orbits the Sun, has enough mass for self-gravity to make it roughly spherical, and has cleared its orbital neighbourhood of other debris. That definition was constructed for our solar system and becomes complicated to apply to objects around other stars, where the gravitational context is completely different. For objects beyond our solar system, the OWL has proposed using the deuterium burning limit as the dividing line between planets and brown dwarfs. Deuterium is an isotope of hydrogen. At masses above roughly 13 times Jupiter's mass, an object becomes dense and hot enough in its core to fuse deuterium, a process that releases energy. Objects below that threshold cannot sustain this fusion. The proposal is to call objects above the deuterium burning limit brown dwarfs, and objects below it planets, regardless of how they formed. Roge 1315b's has a mass estimated at roughly 1 to 2 times Jupiter's mass. It is well below the deuterium burning threshold. By the mass-based definition, it is a planet. But mass and size tell different stories here. The planet's radius is close to twice Jupiter's. Its volume is close to 8 times Jupiter's, yet its mass is only 1 to 2 times Jupiter's. That means its density is dramatically lower than Jupiter's. Where Jupiter averages about 1.3 grams per cubic centimetre, which is very close to the density of liquid water, Roge 1315b is far less dense. Its average density is only a small fraction of water. It is, in a real physical sense, an enormous object made of very little stuff. Imagine inflating a balloon to 8 times its normal size without putting any more air inside it. The balloon would be enormous, but it would also be extremely thin-walled. Roge 1315b's is something like that, except the thin walls are a gas giant's atmosphere, stretched and bloated by stellar heat until the outer layers are barely holding on against the planet's weak surface gravity. There are objects in the universe less dense than water. Some of the most extreme hot Jupiters have densities lower than styrofoam. They are held together not by rigid structure, but by gas pressure and gravity, the same forces that hold any gas giant together, but stretched to a regime where the gas has been heated to the point that it occupies vastly more volume than it would in a cooler state. The largest known planet is, in a meaningful sense, mostly hot, thin gas. It is worth sitting with that for a moment. The object with the largest confirmed radius in the catalogue of known planets is not a solid world. It is not a world with a surface you could stand on. It is an enormous sphere of heated gas, its outer layers barely contained by gravity that is weaker than Jupiter's cloud tops, despite the planet being far larger. The internal layers are compressed by the weight of everything above them, but the outer layers are held so loosely that they drift away into space at a measurable rate. This is what the title of this script means. The most horrifying thing about the size of the largest planet is not just the number, it is what the number represents. Something immense but thin, something vast but fragile, something enormous by any human measure but barely hanging together at its edges. When astronomers look at the properties of hot Jupiters as a group, the pattern of inflation is clear. Planets that orbit closer to their stars tend to be larger for a given mass. The correlation is not perfect, but it is real and statistically strong across the known population. The irradiation from the star pumps energy into the planet's atmosphere, the atmosphere resists contraction, and the planet stays inflated. The more intense the irradiation, the more inflated the planet tends to be. This is the general pattern. What makes Roge 1315b notable is where it sits within that pattern. Its radius is not just above average for its mass, it is at the high end of all measured radii. The combination of its irradiation level, its mass, and its resulting size places it among the most inflated planets confirmed. The mechanisms that drive inflation are still a subject of active research. The basic picture is agreed upon. Stellar irradiation deposits energy into the planet's atmosphere. That energy counteracts the cooling and contraction that would otherwise shrink the planet over time, and the planet stays large. But the details of how exactly the stellar energy gets transported downward into the deep atmosphere, and how much of it contributes to sustained inflation versus being radiated back into space, are less settled. The difficulty is that the interior of a gas giant is not accessible to direct observation. What we know about the interiors of gas giants comes from models constrained by observations of radius, mass, and in some cases magnetic field properties. The interior structure is inferred, not measured, and the models have to explain both the general correlation between irradiation and inflation and the specific cases, like Roge 1315b, that sit at the extreme end of the distribution. Several additional mechanisms have been proposed to explain inflation beyond what simple irradiation models predict. One involves a process called ohmic dissipation. Gas at the high temperatures in hot Jupiter atmospheres is partially ionized, meaning some electrons have been stripped from their parent atoms and move freely through the gas. When ionized gas moves through a magnetic field, it generates electrical currents. Those currents flow through the gas, which has electrical resistance, and the resistance converts the current's energy into heat. If the currents penetrate deep enough into the atmosphere, the heat deposited there contributes to the inflation. The magnetic fields needed to drive this process come from the host star and from the planet's own dynamo, the circulation of conducting fluid in its deep interior that generates a planetary magnetic field. Another proposed mechanism involves the kinetic energy of the atmospheric winds themselves. The irradiation drives strong wind patterns in the upper layers of the atmosphere, and those winds carry kinetic energy. A fraction of that kinetic energy can be transported downward by turbulence or wave processes, depositing it at depth where it becomes heat rather than returning to space as radiation. Tidal dissipation is a third proposed contributor. If the planet's orbit is not perfectly circular, even slightly eccentric, the tidal force from the star on the planet varies throughout each orbit. As the planet moves slightly closer to and farther from the star during one orbit, the strength of the tidal distortion changes. The planet's interior flexes in response, and that flexing generates heat through internal friction, just as bending a wire repeatedly warms it at the bend. Even a very small eccentricity can produce a measurable heat contribution if sustained over long timescales. For hot Jupiters, tidal circularization operates over timescales that are often shorter than the age of the system. The same tidal forces that locked the planet's rotation also tend to circularize the orbit, so many hot Jupiters observed today have nearly circular orbits. But if the eccentricity was higher in the past, during the early stages of the system, tidal dissipation during that period could have deposited significant amounts of heat in the interior that is still present today as residual warmth. For the most extreme inflated planets, multiple mechanisms may be operating simultaneously, each contributing a fraction of the total heating needed to explain the observed radius. The end result is a planet that cannot contract to the radius it would have if it were cooler, a planet whose size is maintained by a continuous energy input from the object it orbits. Roge 1315b exists at its current size because its star made it large and continues to keep it that way. The star is not just the light source of this planetary system, it is the sculptor of its largest member. There is a way to think about the relationship between Roge 1315b and its star that illuminates the full strangeness of the situation. In our solar system, the planets formed in the disk surrounding the Sun and then evolved independently. The Sun influences them through gravity, through radiation, through the solar wind, but the planets are in some sense separate entities. They have their own internal processes, their own geological or atmospheric histories, their own future fates that diverge from the Sun's. For Roge 1315b, the separation is less clear. The planet's size is maintained by an ongoing energy input from the star. Remove the star or move the planet to a cooler distance, and the planet would begin to contract toward the radius it would have without stellar inflation, a radius that planetary models suggest would be closer to Jupiter's. The planet's current form is not a property of the planet alone. It is a property of the planet in the presence of that specific star at that specific distance. In a real sense, the star is not just illuminating this planet. The star is participating in the planet's physical state right now, in an ongoing way, through the continuous flow of energy from the star's surface into the planet's atmosphere. The planet and the star are more deeply coupled than anything in our solar system. This coupling will continue for as long as the star is on the main sequence. Billions of years. Long enough that the concept of human time becomes useless as a measure. The planet has been in this relationship with its star for longer than Earth has existed, and will continue in it for longer than the remaining lifetime of the Sun. Consider what has happened on Earth during the time Roge 1315b has been in its current state. The oceans formed, the first single-celled life appeared, the first oxygen accumulated in the atmosphere, multicellular organisms evolved, the first animals, the first land plants, the explosion of animal diversity, the dinosaurs, the mass extinction, the mammals, the primates, Homo sapiens, every human civilization, every scientific revolution, every discovery humanity has ever made. All of that happened on Earth during the time Roge 1315b has been completing its 3-day orbit, silently, continuously, in the same tight path around its star. The planet does not experience this time in any meaningful sense, it simply orbits. But the timescale speaks to how deeply the planet and the star are intertwined. What we are observing now is not the beginning of a process. It is a snapshot of something that has been running for a duration that has no human equivalent. Roge 1315b's was already the size it is before the first vertebrates crawled onto land. The coupling is old. It will continue. There is a number that sometimes comes up in discussions of hot Jupiters that reframes everything. The surface gravity. Surface gravity is the acceleration an object at the surface, or in the case of a gas planet at the outer atmosphere, would feel pulling it downward toward the centre. On Earth, surface gravity is approximately 9.8 meters per second squared. That number is so familiar it barely registers. It is what keeps you in your chair. It is what makes a dropped object fall. It is the constant background against which everything you have ever experienced physically has taken place. On Jupiter, the surface gravity at the cloud tops is about 25 meters per second squared, roughly 2.5 times Earth's. A person standing on a hypothetical platform at Jupiter's cloud level would feel 2.5 times their Earth weight pressing down. The planet's greater mass more than compensates for its greater size, producing stronger gravity than Earth, despite being vastly larger. For an extremely inflated planet like Roge 1315b, the relationship between mass and gravity at the outer atmosphere is different. The planet has only about 1 to 2 times Jupiter's mass, but it has close to twice the radius. Gravity at the outer atmosphere of a planet depends on the planet's mass and on the square of the distance from the centre. If you double the radius while keeping the mass the same, the surface gravity drops to 1/4 of its original value. Roge 1315b's has roughly Jupiter's mass spread across nearly twice the radius, so the gravity at its outer atmosphere is significantly lower than Jupiter's, perhaps only 1/4 to 1/3 of what you would experience at Jupiter's cloud tops. This has a counterintuitive consequence. The planet is enormous, but it does not feel especially massive at its surface. If you were somehow suspended in the outer layers of Roge 1315b's atmosphere, the gravitational pull dragging you inward would be weaker than what Jupiter produces, not stronger. The gas surrounding you at that altitude would be under lower pressure. The escape velocity from that altitude would be lower. It would take less energy to push a parcel of gas from the outer atmosphere of Roge 1315b into space than to push the same parcel from Jupiter's atmosphere into space. This is why the planet's enormous size works against itself. The very inflation that makes it so large also makes it easier for the star's radiation to strip away the outer layers. The atmosphere expands because the star heats it, but the expanded atmosphere sits in weaker gravity, which makes it more vulnerable to being stripped by the same star that expanded it. The planet is not in any short-term danger of being destroyed. Its mass budget is enormous. The rate of atmospheric escape, while measurable, would take billions of years to meaningfully reduce the planet's total mass. But the direction of the process is clear, and it has been clear since the planet arrived at its current orbital position. The star made this planet large. The star keeps it large. And very, very slowly, over timescales no civilization will ever observe in full, the star will take it apart. Whenever an object at this scale is described, it is natural to ask what it would look like. The question is harder to answer than it might seem. Roge 1315b is far away from Earth, orbiting a star in the constellation Draco at a distance of many hundreds of light-years. No telescope operating today can take an image of the planet that resolves it as a disk with visible features. What we know about it comes from the light curve of its transits, the changes in starlight brightness as the planet passes in front of the star, and from spectroscopic measurements that analyze how the star's light is modified as it passes through the planet's atmosphere during transit. From those measurements, astronomers can infer quite a lot about what this world is like. The temperature of the outer atmosphere on the day side, given the irradiation level, would be hot enough to glow faintly in infrared light. This thermal emission is not a reflection of starlight, but radiation produced by the planet's own heat. Some hot Jupiters have been detected not only in transit, but also in secondary eclipse, the moment when the planet passes behind the star. By comparing the total brightness of the star plus planet system just before and after the secondary eclipse to the brightness during eclipse, astronomers can isolate the infrared emission from the planet's dayside alone. This technique has been used to map temperature distributions across the daysides of several hot Jupiters using space-based infrared observatories. From those measurements on similar objects, the picture that emerges for a planet of this temperature and size is of a world that glows a deep, dull red in infrared, with a dayside that would be visible as a thermal glow if you could approach it closely enough. The colour visible to human eyes would depend on the cloud composition. At very high temperatures, cloud layers made of silicate particles, tiny droplets of molten rock suspended in the upper atmosphere, form at altitudes where temperatures have cooled slightly from the extreme below. These silicate clouds scatter and absorb light differently from water clouds, producing dark reddish or ochre hues rather than the bright white of Earth's water vapor clouds. At intermediate altitudes below the silicate cloud layer, where temperatures are even higher, no clouds form at all. The atmosphere is simply hot, clear, compressed gas, glowing in its own heat. There are no rings expected at this orbital distance. Saturn's rings exist because Saturn is far enough from the Sun that the tidal forces do not tear apart the ring material. Close to a star, the tidal forces are far stronger. Any ring material orbiting Roge 1315b would be exposed to powerful stellar radiation and strong tidal gradients that would either drive the particles inward toward the planet or outward away from it, or vaporize them entirely. Rings cannot persist in that environment. There are almost certainly no moons. Moons of hot Jupiters are gravitationally unstable at close orbital distances. The Hill sphere of a planet, the region where the planet's gravity dominates over the star's gravity and a moon can remain bound to the planet, shrinks dramatically as the planet moves closer to the star. At Roge 1315b's orbital distance, the Hill sphere is so small that any moon with a stable orbit would have to orbit extremely close to the planet, far inside where the intense tidal forces would tear it apart. And any moons that may have accompanied this planet during its outer disk formation were almost certainly stripped away during the long inward migration or destabilized by the close encounter with the star. No rings. No moons. One perpetual dayside of scorching heat. One perpetual nightside of fierce winds. The planet alone, completing its tight orbit in 3 days in silence, close to the fire of its star. There is something clarifying about that image. The most complex planetary system we know of, our own, has 8 planets, 5 recognized dwarf planets, hundreds of moons, and billions of smaller bodies arranged in rings, belts, and clouds. Centuries of observation have catalogued the components of the solar system, and missions have visited most of the major bodies. The solar system is rich with structure. Roge 1315b's system, by comparison, is stripped to the minimum: 1 star, 1 planet, and the bond between them. The minimum turns out to be enough to produce a planet larger than anything in the solar system. It is enough to produce a world with atmospheric chemistry more extreme than anything we have studied up close. It is enough to create conditions that force astronomers to develop new physical models and test them against observations. The stripped-down system and the maximum-sized planet are, as this script has described, connected. The emptiness of the inner system and the enormousness of the single surviving planet are 2 consequences of the same history. You cannot understand why the planet is this large without understanding why it is this close. And you cannot understand why it is this close without understanding the migration that cleared the inner system. The extreme and the empty go together. it is worth stepping back from the specific measurements and asking a broader question. What does the existence of a planet like this tell us about the universe? There is something else that transit measurements reveal beyond size. When a planet passes in front of its star during a transit, some of the starlight filters through the outermost layers of the planet's atmosphere before reaching our telescopes. That filtered light has passed through gas, and as it did, the different molecules and atoms in the gas absorbed specific wavelengths of light, leaving dark gaps in the spectrum. Those gaps are fingerprints. Each element and molecule absorbs a unique set of wavelengths, a chemical signature that can be read from the pattern of absorption features. This technique, called transmission spectroscopy, has become one of the primary tools for studying the composition of exoplanet atmospheres. For hot Jupiters, which have large atmospheres and pass in front of bright nearby stars, the technique works especially well. The large atmospheric scale height, the vertical distance over which the atmospheric pressure changes by a factor related to temperature and gravity, means the atmosphere presents a thick ring of absorbing gas around the planetary disk during transit, making the spectroscopic signal easier to detect. The James Webb Space Telescope, launched in December 2021 and operating at full capacity since 2022, has transformed what is possible in this area. Its infrared sensitivity and spectroscopic capabilities have allowed detailed chemical mapping of hot Jupiter atmospheres at a level not previously achievable. Water vapor, carbon dioxide, carbon monoxide, sulfur dioxide, and various hydrocarbon molecules have been detected in different hot Jupiter atmospheres with JWEST. These detections are not just interesting chemistry. They constrain the temperature profiles, the circulation patterns, and the formation histories of the planets being studied. For the most highly irradiated hot Jupiters, the high temperatures in the atmosphere create conditions where molecules are torn apart by the heat. Water molecules dissociate into hydrogen and oxygen at high enough temperatures. This thermal dissociation and recombination cycle, where molecules break apart on the hot day side and reform on the cooler night side, can itself drive winds and influence the atmospheric circulation in ways that affect what spectroscopy detects. The atmosphere of Roge 1315b, at its extreme irradiation level, is expected to be hot enough that many molecules are either dissociated or simply absent as condensed species. The dayside atmosphere at the temperatures involved approaches conditions more like a stellar atmosphere than a planetary one, at least in terms of temperature. The spectroscopic signatures expected from such a world would be dominated by atomic absorption features rather than the molecular features more typical of cooler gas giants. What the atmosphere of this planet looks like in its spectroscopic fingerprint, and what that reveals about its composition and structure, is a question that better instruments and more observation time will continue to refine. The planet is already giving answers to anyone patient enough to collect and interpret the light. This is one of the quieter revolutions that the transit method has enabled. Planets around other stars, which are themselves too faint and too distant to image directly, are nonetheless revealing their atmospheric chemistry through the spectroscopic signal they imprint on the starlight that filters through them. We know what is in the atmosphere of worlds we cannot see, because we can read the fingerprint they leave on the light we can measure. For Roge 1315b specifically, detailed spectroscopic analysis is ongoing. The planet is a good target for atmospheric characterization because of its large radius, which creates a large atmospheric signal, and because it orbits a relatively bright star compared to the faint background. Each transit provides another spectrum to add to the accumulating dataset. Each additional observation improves the signal-to-noise ratio and allows weaker absorption features to be identified. Ultimately, What the spectroscopy reveals is a constraint on where this planet came from. The composition of its atmosphere, the ratio of carbon to oxygen, the presence or absence of certain molecules, can be compared to models of disk chemistry at different orbital distances. Different formation locations produce different atmospheric compositions, and those compositional signatures are partially preserved even after migration. By reading the chemistry of an atmosphere, astronomers can read clues about where the planet formed before it moved. In this way, the atmosphere of Roge 1315b may eventually tell us not just what the planet is made of, but where it was born. Exoplanet astronomy began in earnest in the 1990s, when the first confirmed detection of a planet around a main sequence star was made. Michel Mayor and Didier Queloz, using a spectrograph at the Observatoire de Haute-Provence in France, measured the radial velocity wobble of the star 51 Pegasi and found a clear periodic signal indicating a companion object with roughly half Jupiter's mass, completing an orbit every 4 days. The detection was confirmed by Jeff Marcy and Paul Butler at the Lick Observatory within weeks. Mayor and Queloz were awarded the Nobel Prize in Physics in 2019 for the discovery. That first detection immediately unsettled the models. A half-Jupiter mass planet completing one orbit every 4 days around a Sun-like star was not something the prevailing planet formation theories predicted, and it was very close to its star, in a place where a gas giant should not have been able to form. In the decades since, the inventory of known planets has grown to thousands, and the diversity of that inventory has consistently outpaced what theorists expected. The exoplanet population contains not just hot Jupiters but super-Earths, mini-Neptunes, water worlds, lava worlds, ultra-short period planets with orbital periods measured in hours, and planets in multiple star systems that were thought to be dynamically unstable. Nearly every category of planetary object that theorists said should not exist has turned out to exist in some form. The radius inflation of hot Jupiters was one of these surprises. As transit surveys measured the sizes of hot Jupiters in larger numbers, it became clear that a substantial fraction of them were larger than predicted for their masses, not marginally larger. In some cases, dramatically larger. The inflation mechanisms had to be developed after the objects were discovered, not before. The universe produced objects the models had not anticipated, and the models then had to catch up. Roge 1315b represents the current outer edge of that distribution, the largest measured planet, the most extreme case of a general phenomenon that was itself unexpected. It is the end of a chain of surprises that began the moment the first exoplanet was confirmed. What this suggests about the universe is not simple to summarize in one sentence. It suggests that the conditions under which planets form and evolve are more varied than the constraints of our single solar system would imply. It suggests that the parameter space for planetary configurations is wider than early models assumed. And it suggests that whenever astronomers have thought they understood the outer limit of something, the universe has occasionally produced an example that exceeds it. There are over 5,000 confirmed exoplanets in the current catalogues. New ones are added regularly as missions continue and as archive data is reanalyzed with better algorithms. The surveys sample only a small fraction of all the planetary systems in the galaxy. There are hundreds of billions of stars in the Milky Way alone. The confirmed sample is tiny relative to the population it represents. Whether something larger than Roge 1315b exists somewhere in that vast unsampled territory, no one currently knows. The transit method is most sensitive to large planets with short orbital periods, which is why hot Jupiters are among the easiest exoplanets to detect despite their rarity in the overall population. There may be inflated giants in longer orbits, or around stars not yet carefully surveyed, that exceed what we have currently measured. The current record holder may be a record holder simply because those are the planets we have been best equipped to find. The existence of hot Jupiter systems like the one Roge 1315b inhabits raises a question that became significant once the exoplanet population grew large enough to analyse statistically. Hot Jupiters are almost never found with other planets in their systems. In our solar system, Jupiter coexists with many other planets at a range of orbital distances. Jupiter's presence shaped the architecture of the entire solar system, but it did not exclude other planets from forming. The inner solar system has 4 rocky planets. The outer solar system has 3 other giants. The asteroid belt sits in the gap between the inner and outer planets. Hot Jupiter systems look different. When surveys search for additional planetary companions to known hot Jupiters, the inner regions of those systems are generally empty. The orbital zones that would correspond to where Earth, Venus, and Mercury are in our solar system appear to be cleared out in systems with hot Jupiters. The reason, most researchers believe, is the migration itself. When a giant planet migrated inward through the disk from the outer system to its current close-in position, it did not pass through the inner disk without consequence. The migrating giant gravitationally scattered material in the inner disk, stirring up the orbits of smaller bodies, pushing some inward to be accreted by the star, and sending others outward. The migration of a giant planet through the inner disk is a destructive process for any rocky planets or planetary embryos that were forming there. By the time the giant planet arrived at its close-in orbit, the inner disk had been thoroughly disturbed. Any rocky planets that might have formed there were either destroyed, scattered, or had their formation interrupted. The hot Jupiter sits close to its star in a system that is, in the inner regions, largely empty of other planets. This has an implication that runs beyond planetary science. If hot Jupiter migration destroys the conditions needed for rocky planet formation in the inner system, then systems with hot Jupiters are unlikely to also host terrestrial planets at habitable distances from their stars. The presence of a hot Jupiter may be a marker for the absence of the kind of rocky inner planets that might support complex chemistry or life. Our solar system, notably, does not have a hot Jupiter. Jupiter is far from the Sun. It may have migrated somewhat in the early solar system, but not all the way into the inner solar system. The rocky planets of the inner solar system exist because Jupiter stayed in the outer system. The grand architecture of our solar system, the inner rocks and the outer giants arranged as they are, may not be the most common outcome of planet formation. But it may be the outcome that allows for rocky planets in the inner system, and all that follows from them. Roge 1315b's system is a different kind of place. One giant, one star, and the space in between largely cleared by the same process that put the giant where it is. Whether any remnant rocky bodies persist in distant orbits, or whether the disk beyond the giant harbours any smaller companions, is an ongoing question for future surveys. But the inner system, the region where habitable worlds might form, is very likely empty. This is worth sitting with. The solar system we grew up in, the one that defines our intuition for what a planetary system looks like, is in some ways an unusual configuration. It has 4 rocky inner planets. It has an asteroid belt. It has 4 outer planets, including 2 gas giants that stayed in the outer system. It did not produce a hot Jupiter. Whatever migration occurred in the early solar system was limited enough that the inner system remained intact. Planetary science now has to grapple with the fact that this configuration is not the only possibility, and that many planetary systems went through a process that was more destructive to their inner regions. The hot Jupiter systems, with their cleared inner disks and their single dominant giant in a close orbit, represent one outcome. Our solar system represents another. The exoplanet surveys are revealing just how many outcomes are possible and how different they can be from the template we started with. Rogue 1315b's is the extreme of one of these outcomes. The largest planet we have confirmed sits in a system shaped by the most dramatic migration we understand. The size and the orbital position are not independent. Both are consequences of the same history that started with a gas giant forming far from its star and ended with that giant orbiting close enough to be inflated to a size that required new science to explain. The evidence for Rogue 1315b comes down to a graph. A light curve is a plot of a star's brightness over time. For a star with no transiting planet, the light curve is flat. The brightness is constant, or very nearly so, varying only with the slow intrinsic variability of the star itself. For a star with a transiting planet, the light curve shows a periodic dip. At the moment the planet begins to cross the face of the star, the brightness starts to drop. As the planet moves fully onto the disk, the brightness reaches its minimum. As the planet begins to exit the disk, the brightness begins to recover. When the transit is complete, the light curve returns to baseline. The shape of that dip contains the measurements. The depth of the dip, how far the brightness drops from baseline, gives the ratio of the planet's area to the star's area. If the planet has twice the radius of the star's disk, the planet blocks 4 times more light. The math is straightforward. The ratio of the squared radii gives the fractional drop in brightness. For Rogue 1315b, the transit depth is deep enough to be unambiguous. A significant percentage of the star's total light blocked during each transit. The duration of the dip, from first contact to last contact, combined with knowledge of the star's size and the planet's orbital speed, gives the geometry of the transit. A planet crossing the full diameter of the star produces a longer transit than a planet crossing near the edge. A planet in a fast orbit crosses the disk more quickly than a planet in a slow orbit. From the duration and a few orbital equations, the orbital distance and inclination can be derived. The shape of the ingress and egress, the leading and trailing edges of the dip, gives information about the planet's limb darkening, how the planet's disk appears darker toward its edges than at the center as a result of seeing through different depths of atmosphere at different positions. Every transit is another data point. Hundreds of transits observed over multiple observational campaigns refine the measurements. The orbital period is known to high precision from the timing of transits. The radius ratio is refined from the average of many transit depths. The orbital parameters are constrained from the full ensemble of measurements. This is the data that established Rogue 1315b as the largest known planet. Not a single dramatic observation, but an accumulation of light curves, each one a tiny dip in a star's brightness, collectively building a measurement precise enough to calculate the radius to within a small percentage of the true value. The largest planet we have found revealed itself in the quiet language of dimming starlight. In the patient reading of light curves, in the signal to noise of telescopes measuring a distant star's brightness to fractions of a percent, observation after observation, transit after transit, until the number emerged from the data with enough confidence to be published and accepted. The planet is enormous. The signal that found it is subtle. There is something appropriate about that. The subtlety of the signal is also a reminder of the precision required. A transit depth of several percent sounds like a lot compared to the 1/100th of a percent that an Earth-sized planet would produce. But measuring it still requires photometric precision that was not routinely available until space-based observatories eliminated the blurring effects of Earth's atmosphere. Ground-based telescopes were limited in how precisely they could measure stellar brightness because the atmosphere introduces noise. Space-based telescopes operate above the atmosphere and can achieve the photometric stability needed to detect even smaller transit signals. The investment in space-based photometry that produced Kepler, TESS, and the spectroscopic follow-up infrastructure that allowed thousands of transit candidates to be confirmed with mass measurements represents decades of scientific planning, technological development, and funding decisions. The discovery of Roge 1315b and the characterization of its extreme size are outcomes of that investment. The light curves that revealed this planet are sitting in archives, available to researchers, continuing to yield information as analysis techniques improve. This is how modern astronomy works. Observations are collected and archived. Analysis tools improve over time. Objects discovered years ago are reanalyzed with better methods and yield information that was not extractable when they were first found. The data from Roge 1315b's transits that was collected in the years around its discovery is more valuable now, with better atmospheric models and better spectroscopic interpretation techniques, than it was when the first paper was published. To make Roge 1315b's size real, it helps to go through the solar system carefully. Mercury is the smallest planet, with a radius of about 2,440 kilometers. It is smaller than some moons in our solar system. Ganymede, Jupiter's largest moon, has a radius of about 2,630 kilometers and exceeds Mercury in size. Titan, Saturn's largest moon, has a radius of about 574 kilometers, and is almost as large as Mercury. This is one of the small but notable facts of solar system geography. The largest moons of the gas giants are larger than the smallest planet. Mercury itself is rocky, dense, and close to the Sun. It has a thin atmosphere that barely qualifies as one, a surface heavily scarred by impacts accumulated over billions of years, and a peculiar day-night cycle in which one Mercury day lasts approximately 176 Earth days, while one Mercury year lasts only 88. The Sun rises, moves slowly across the sky, and sets over a period that covers 2 full orbits of Mercury around the Sun. Hundreds of thousands of Mercuries would fit inside Roge 1315b. Venus is next, with a radius of about 6,050 kilometers. It is the closest to Earth in size of any planet in the solar system, sometimes called Earth's twin. But Venus is a difficult twin. Its atmosphere is nearly 100 times denser than Earth's and composed primarily of carbon dioxide with clouds of sulfuric acid. The surface temperature is over 460 degrees Celsius, hot enough to melt lead, sustained by a runaway greenhouse effect. Despite these conditions, Venus is small on the scale being discussed here. Over 100,000 Venuses would fit inside Roge 1315b. Earth has a radius of about 6,370 kilometers. The planet you are standing on, with its oceans and atmosphere and the thin surface layer where all known life exists, would fit inside Roge 1315b over 50,000 times. 50,000 Earths. That number should be difficult to absorb because it is genuinely large. It is larger than the number of years that have passed since modern humans first appeared. Mars is smaller than Earth, with a radius of about 3,390 kilometers. It is the planet most discussed in terms of human expansion, the target of multiple active missions, the subject of decades of planning and research. 150,000 Mars-sized objects would fit inside Roge 1315b. The outer planets are a different category. Uranus and Neptune are called ice giants, a term that refers to their bulk composition, which is dominated by water, methane, and ammonia ices rather than hydrogen gas the way Jupiter and Saturn are. Their radii are about 25,000 and 24,000 kilometers respectively. They are large compared to the rocky inner planets, roughly 4 times Earth's radius each, but they are not gas giants in the Jupiter sense. They have smaller hydrogen envelopes surrounding their icy interiors, and they are significantly more dense than Jupiter or Saturn. Uranus is the colder of the two, with the coldest upper atmosphere of any planet in the solar system at about negative 220 degrees Celsius, despite being closer to the Sun than Neptune. This is thought to be because Uranus's internal heat source is effectively zero, unlike Jupiter, Saturn and Neptune, which all radiate more heat than they receive from the Sun. Uranus appears to have almost no excess heat leaking from its interior. Why Uranus is so internally cold compared to the other giant planets is an open question. On the scale of Roge 1315b, Uranus and Neptune each fit inside it roughly 150 times. Saturn, with a radius of about 58,000 kilometers, is the second gas giant, and one of the most distinctive objects in the solar system because of its ring system. Saturn's rings extend outward to about 137,000 kilometers from the planet's center, nearly twice Saturn's own radius, and span a width of about 70,000 kilometers, yet they are only about 20 to 200 meters thick. They are made almost entirely of water ice particles, with some rocky material, ranging in size from tiny grains to chunks several meters across. The rings are thought to be geologically young, possibly forming only a few 100 million years ago, long after the solar system's main formation phase. 80 or so Saturns would fit inside Roge 1315b. The rings, which span such an impressive distance around Saturn, would themselves fit inside Roge 1315b's diameter, with room to spare. Jupiter, with a radius of about 71,000 kilometers, is the largest planet in the solar system. 8 Jupiters fit inside Roge 1315b. That progression from Mercury to Earth to Saturn to Jupiter to Roge 1315b covers an enormous range. It covers the full diversity of planetary sizes known in the solar system, and then goes beyond it. The final step, from Jupiter to Roge 1315b, is itself a doubling in radius and an 8-fold expansion in volume. Jupiter, which already seemed like the limit, is revealed by comparison to be not the limit at all. This is the scale ladder that leads from anything you can intuitively grasp to something you have to reason your way through. You cannot feel the size of Roge 1315b. You can only build toward it, step by step, using comparisons to things you know, and arrive at the conclusion that the number is correct even if the number does not land with full force. It might help to try one more comparison. The diameter of Roge 1315b is roughly 280,000 kilometers. The distance from Earth to the Moon is about 384,000 kilometers. This means that Roge 1315b's diameter is about 3/4 of the Earth-Moon distance. If you placed this planet where Earth is, and the Moon were in its normal orbit around Earth, the Moon would be only about 50,000 kilometers beyond the planet's outer atmosphere. The Moon, which to our eyes is a distant world, would be just above the cloud tops of this planet. That is the scale of what the universe has produced. Not just large. Large enough that the gap between the surface of the planet and the orbit of a moon would be smaller than the planet's own radius. The largest planet we have found is not just large by human standards, it is large by planetary standards. It exceeds the largest object in a solar system of 8 planets, 2 of which are already gas giants, by a factor that required planetary science to develop new explanations rather than simply scale up old ones. And the way it became that large, through stellar irradiation maintaining an inflated atmosphere that the planet's own weak surface gravity cannot pull back to smaller size, means that the size is not really a property of the planet alone. It is a property of the planet and the star together, a shared condition sustained by their proximity. There is a final scale comparison worth making before this night closes. The Sun has a radius of about 696,000 kilometers. Jupiter's radius is about 71,000 kilometers, roughly 1/10 the Sun's. Roche 1315b has a radius of roughly 140,000 kilometers, close to twice Jupiter's and close to 1/5 the radius of the Sun. That last comparison has a strange quality to it. Roche 1315 is a planet confirmed by the definition used for such objects. Its mass is planetary. But its radius is approaching 1/5 of the radius of a typical Sun-like star. It sits between the familiar categories in a way that highlights how the categories were built for the objects we already knew, and how the universe does not necessarily respect them. Now consider what that size means at the orbital distance where this planet lives. At its tight orbital radius, the planet is close enough to its star that the star's disk, as seen from the planet's outer atmosphere, would be enormous. From Earth, the Sun subtends about 1/2 a degree in the sky, a disk small enough that you can comfortably cover it with your thumb held at arm's length. From Roche 1315b's dayside, the star would fill not 1/2 a degree, but many degrees of sky. It would not be a point or a small disk, it would be a looming immense presence. Filling the sky near the horizon with the churning plasma of a stellar photosphere, its surface granulation visible as a boiling texture, its limb darkening perceptible as a rim slightly cooler and darker than the centre. And it would never move. The star would be fixed in the sky from the dayside, permanently above the same region of the planet, because the planet never rotates relative to its star. The star is always there. It is not a visitor. It is a permanent fixture at the top of the atmospheric column, directly overhead on one face of the world. From the night side, the star is never visible at all. Only the darkness, only the wind, only the slow infrared glow from the dayside leaking around the planetary limb, visible as a faint rim of warmth at the edge of the world where the Terminator runs. This is a planet with no neutral zone, no temperate morning, no gradual dawn, just the absolute of permanent fire on one side and the absolute of permanent darkness on the other, and a roaring wind blowing heat from one hemisphere to the other along the boundary between them. Nothing in our solar system is like this. Not Jupiter, not Mercury, which is close to the Sun by solar system standards but still distant compared to hot Jupiters and not tidally locked to the Sun. Not any object in the catalogue of things we grew up calling planets. Roche 1315b is not a scaled-up version of a familiar world. It is a genuinely different kind of object, a category of world that the universe is apparently comfortable producing, even though it produced nothing like it in the one planetary system we had direct access to for most of human history. Scale is the first shock. The inflation is the second. The tidal lock is the third. And the last is simply the reminder that this is what a planet can be, under the right conditions. The conditions exist. The planet happened. The universe did not require our permission or our expectations. The history of astronomy is largely a history of corrected assumptions. The Earth was not the centre. The Sun was not the centre. The Milky Way was not the only galaxy. The galaxies were not arranged uniformly. The universe was not expanding at a constant rate. Each of those corrections required observations that contradicted the prevailing model, followed by a period in which the model was rebuilt to fit what had been seen. The corrections were never comfortable at the time, and always look obvious in retrospect. What makes the exoplanet corrections slightly different is the speed at which they accumulated. The shift from geocentrism to heliocentrism took centuries of argument. The recognition that the Milky Way was just one of many galaxies took decades to become broadly accepted after the relevant measurements were made in the 1920s. The exoplanet revisions happened within a single human career. A researcher who started graduate school in planetary science in the mid-1990s, when the first hot Jupiters were being found, worked through the entire revision in the period from their student years to their professional prime. The revision was rapid because the data was abundant. Transit surveys measured hundreds of planets. Statistical patterns emerged. The field had to revise its models not once but several times as different surprises appeared in the data. Hot Jupiters, inflated radii, the radius gap in the sub-Neptune population, the occurrence rates of different planet types. All of these patterns were not predicted by early models, and all of them required model updates. ROG 1315b appeared in this context, a single extreme object whose existence represented the outer boundary of one of those patterns, the inflation pattern, pushed to a radius that no model had predicted before the data forced it to be explained. What the exoplanet era has repeatedly demonstrated is that the solar system is an inadequate sample size for understanding planetary systems in general. We had one system. We built models from it. The models were internally consistent and explained what we saw, but they were built from a sample of one, which is a weak foundation for a general theory. Every additional system found since 1995 has added a new data point, and a significant fraction of those data points have been surprises. Hot Jupiters surprised us. Their inflation surprised us. The diversity of planet sizes in the sub-Neptune range surprised us. The common occurrence of super-Earths, which have no analogue in the solar system, surprised us. The architecture of compact multi-planet systems, with several planets orbiting interior to Mercury's orbital distance, surprised us. The surprises are not a sign that astronomy is failing. They are a sign that astronomy is working. Each surprise is a new constraint on the theory. Each new constraint produces a more complete and more accurate understanding of what planetary systems can be. ROG 1315b's is the most extreme constraint on one specific parameter, the maximum radius a gas planet can reach under stellar irradiation. That constraint is now known to be roughly twice Jupiter's radius, and the physics that explains it, while still being refined in its quantitative details, is understood well enough to be taught as established science. The discovery of hot Jupiters and the subsequent discovery of inflated hot Jupiters, and the eventual detection of ROG 1315b at the outer edge of what has been measured, follows the same basic pattern at a smaller scale. The model said gas planets should cap out at roughly Jupiter's size. Inflation from stellar irradiation was not in the original models. When the first inflated hot Jupiters appeared in transit surveys, they were initially checked carefully for systematic errors before the inflation was accepted as real. Then, the models were extended to explain it. The extension works mostly for the objects in the middle of the distribution. The objects at the extreme edge, the ones most dramatically inflated, still resist fully clean theoretical explanation. Not because the basic physics is wrong. Because the quantitative details of how exactly stellar energy gets transported into a gas giant's deep interior remain incompletely understood. The models get the direction right, they struggle with the magnitude at the extremes. This is not a failure of science, it is science working correctly. You observe. You model. The model fails at the edges. You extend the model. You observe again. The edges move. ROG 1315b's sits at the current edge. It is the most extreme example confirmed. It may eventually be exceeded by something larger, found by a better survey with a more sensitive instrument. The Plato mission, planned by the European Space Agency, will survey hundreds of thousands of stars for planetary transits with sensitivity beyond what current missions provide. Future surveys will find more planets and find more extreme examples within those populations. Or it may be that Roge 1315b sits at a genuine physical ceiling, a place where stellar inflation has done as much as it can do before the planet's gravity begins to resist further expansion and mass loss begins to reduce the total atmospheric volume. Either way, it already tells us something about what the universe is willing to do. The universe is willing to make a planet so large that 8 Jupiters fit inside it. A planet whose outer atmosphere barely holds on under gravity weaker than Jupiter's cloud tops, despite the planet being twice Jupiter's size. A planet permanently locked in orbit around a star so close that its day side glows in infrared, and its night side is torn by winds reaching thousands of kilometers per hour. A planet that formed far from its star, was dragged close by the mechanics of disk migration, and then spent billions of years being slowly inflated by the heat of the thing it cannot escape, and slowly eroded by the radiation of the same thing keeping it large. The universe made this. Without announcement, without intent. Around a star in the constellation Draco, while Earth's oceans were forming and life was beginning to figure itself out somewhere else, a planet was being built, dragged inward, and inflated to a size that no one on Earth had yet imagined was possible. Because no one on Earth existed yet to imagine anything. And then, billions of years later, a civilization on a small rocky planet developed instruments sensitive enough to detect the shadow of this planet crossing its star. They measured the dimming to fractions of a percent. They converted that dimming into a radius, and the radius into an understanding of what physical conditions could produce it. They found that the universe had made something larger than their models had anticipated, at a location they could point to in the sky, in a direction where a dragon was once drawn, and at a distance they could calculate. The universe did not wait for us to imagine it first. It made Roge 1315b anyway. On a clear night, if you know where to look, you can find the constellation Draco. In the northern hemisphere, Draco wins between the Big Dipper and Cassiopeia, a long sinuous shape made from stars that ancient Greek astronomers traced as a dragon and named Draco after. It is one of the largest constellations by area, but most of its stars are faint, and it lacks the dramatic bright centre of constellations like Orion or Scorpius. It is a patient constellation. You have to look for it. The constellation is circumpolar in the northern hemisphere, meaning it never fully sets below the horizon at latitudes above roughly 30 degrees north. It is visible on any clear night, year-round, slowly rotating around the north celestial pole. The star at the tip of Draco's tail, a star called Thuban, was the North Pole star roughly 5,000 years ago, during the time of ancient Egypt, because the Earth's axis wobbles slowly over a 26,000-year cycle. The sky changes, even if slowly. Somewhere in the direction of Draco, at a distance of hundreds of light years, a star is burning. Its light is reaching Earth right now. Mixed into the collective faint glow of that region of sky, indistinguishable to the naked eye from thousands of other stars, the photons from that particular star are arriving. And close to that star, a planet circles in 3 days, completing orbit after orbit in the heat and silence of deep space. Think about what 3 days means on the scale of this planet's lifetime. If the system is 4 billion years old, and the planet has been in this close orbit for most of that time, it has completed roughly 500 billion orbits. 500 billion 3-day cycles around its star. Every revolution, the same day side facing the same star, the same night side facing the same dark. Every revolution, the stellar wind eroding a little more of the outer atmosphere. Every revolution, the same winds tearing around the terminator. The planet has never seen a sunset. It has never experienced a change in the position of its star. Its night side has never seen a dawn. The winds on its terminator boundary howl at speeds that no storm on Earth can match. Its outer atmosphere reaches temperatures that would destroy any material humans have built or worked with. And its size, its quietly enormous, barely gravitationally held together size, exceeds anything that formed in our own solar system. The planet does not know it is being observed. The star does not know astronomers have given its planet a designation. The system continues regardless of whether anyone in the galaxy is aware of its existence. It simply orbits. Every 3 days, holding its enormous, thin-walled self together against the radiation that made it large and is slowly dismantling it, carrying the fingerprint of its inflation in every transit signal that passes through the telescopes of a civilization on a small rocky planet 330 light-years or more away. We found it. We measured it. We gave it a name, and now the outer edge of what we know about how large a planet can be has a number attached to it, a location in the sky, and a place in a catalogue of objects the universe has produced that we are still learning to read. Look toward Draco tonight if the sky is clear. The constellation is there, year-round in northern skies, patient and faint. The largest known planet is in that direction. Good night.